Eduardo Teixeira. Eduardo Teixeira, I think that I'm taking a look in this audience. I think that most of you is aware about his work on PDEs. And indeed, he is one of the winners of the Prize for Americas. And he's got his PhD in 2005 under the guidance of Luis Caffarelli. And currently, he is a full professor at the University of Federal of Ceará. And his main field of research concerns PDEs and their applications, but his broad interest involves free boundary theory, harmonic and geometry analysis, among others. And Teixeira's recent works deal with geometry-free boundary problems, sharp regularity theory for elliptic problems, fully non-linear EMAB problems, singular PDEs, etc. All top and relevant themes of research. In addition to an outstanding research career, he also made a significant contribution towards the development of mathematics science in Brazil, especially in the northeast part of our country. Besides his use, he is a leading figure in analysis and PDE research group in Fortaleza, a school that has been rapidly growing to become a reference in Brazil and Latin America. And more information about Eduardo, you can check in that little book that distributed in the inaugural conference here. And then now, please, Eduardo.
Okay, thank you. Thank you, Zezé. Thank you for this kind introduction. So good morning. So I would like to start by thanking the organizing committee. For me, it's a great, great pleasure to be here in Guanajuato as an invited speaker and one of the winners of the MCA prize. Okay, so this is the plan of my talk. I will give this talk was designed for a very general audience, okay? So I apologize for the experts. So I start with a very crash course on second order elliptic PDEs. So basically, very general, broad overview. And then we'll do a tour through the free boundary problems. And in the last part of my talk, I intend to show to you what we have been doing by importing some of the free boundary technologies to study some classical problems in elliptic and parabolic PDEs. Okay, so let me start by introducing our old friend, the Laplacian. So the Laplacian is this operator, this second order operator that computes the second pure derivative of u and ab the map. So the Laplacian can be seen in two ways. It's either the divergence of the gradient or the trace of the Hessian. Okay? So once you understand the Laplacian as the divergence of the gradient, you are taking into account energy considerations. So it's a variational theory. And if you see the Laplacian as the trace of the Hessian, this is a non-variational theory. Okay? It's in non-divergence form. So, I mean, there has been a lot of talks in this conference about equations, and the Laplacian appears everywhere. So, probably in our studies, the first time that we see the Laplacian, maybe we don't even look at as the Laplacian, but it's from the Cauchy-Riemann equations when you do the first course in complex analysis. Okay? So it comes from the Cauchy-Riemann equations that the real and imaginary part of holomorphic functions are harmonic. It solves Laplacian of u equals to 0. And that justifies the miracle that happens in that course, that you start by defining a holomorphic function as a one differentiable function, and 3-4 lectures later, the function becomes analytic. It has power series and so on and so forth. So this is one of the reasons that happens. Okay, but the Laplace appears in many other contexts from mathematical fields, for instance, in the theory of elastic membranes, when it accounts to minimize the integral of the gradient square, and in fluid mechanics and many other places, differential geometry and so on and so forth. But let me just point out, Luis Caffarelli did that in his talk, in his plenary talk, but let me return to that issue of diffusion. Okay, so Laplace is a model for diffusion, and I'd like to stress that a little bit more in this talk. So here's a general question. It's, if one asks how the temperature get adjusted in a stationary situation, what happens is that if you have a point in this room, so what happens is that this point will feel the temperature around it, and it will average it out. Okay, if there is more heat in one side, I will take this heat. If there is other place that is cooler, I'm going to give heat to that place, and so on and so forth. But that is happening, all points are doing that, and in every scale. So at the end, the answer to that question is that T, the temperature at a point X, is the average at every scale of T itself. Okay, so this is how the temperature evolves. So if you put one step forward on these, like writing this in slightly more mathematical terms, you end up with these this equation per se. So T of X is the integral, the average of T itself. Okay, and this is equivalent to saying that T is harmonic. Okay, so in fact, harmonicity can be thought as this property that the function is the average of itself. Okay, so I will return to that in a minute. So as I was saying, the elliptic theory, it divides in two main brands. The first one is when you take energy considerations. So whenever your problem is based on energy considerations, you end up with equations in divergence form. Basically, it comes from the divergence theorem and minimizers and problems in the calculus of variations and so on and so forth. And the equations appears in this format. It's the divergence of some matrix that takes into account the properties of the media that you are modeling your problem, or maybe it's in a Riemannian manifold or so on and so forth. And ellipticity, in an analytic meaning, is that the eigenvalues of this matrix is bounded below and above. Okay? But PDE, elliptic PDE also appears in probabilistic interpretations, and in general this brings us to operators in non-divergence form, which the linear prototype is this, and again ellipticity is the same condition on the matrix, is that it's bounded below and above. Okay? But in this talk, I don't want to see ellipticity as an analytic definition. Or what I would like to see, the way that I would like to interpret ellipticity is more like based on that naive example of the temperature that I mentioned. Okay, so a geometric idea behind ellipticity is that a second-order equation is elliptic if it prescribes a balance on how much the graph of a solution bends towards the different directions. Okay, so if you think a little bit about that example that I mentioned, what happens is that, for instance, if a function to be harmonic, this is the graph of a harmonic function. For a function to be harmonic, if it bends up in one direction, it will have to bend down in another direction to compensate so that the average is precisely the value at that point. Okay, and what is remarkable is that based on this very naive understanding of ellipticity, you can prove regularity estimates. Okay, there are some regularity structure behind this idea. Okay, so just based on this fact or interpreting ellipticity by this general idea, you can prove regularity. So the next step that I would like to talk a little bit is like a very quick overview on the regularity theory for elliptic PDEs. Okay. So the first result that I'd like to mention is the Schauder estimates that goes back to the 1930s, okay, which says that if the coefficients of the problem are Hilbert continuous, so C0 gamma for some gamma between 0 and 1, then two things happen. If you are in a non-divergence form, solutions are C2 gamma, and this regularity is optimal. Of course, this is optimal. I will come back to that in later part of my talk. And in divergence form, it lacks one derivative. So solutions to that equation is just C1 gamma. This result is optimal. It fails if gamma is equal to 1, and it fails when gamma is equal to 0. So it seems that there is no room for improvement. Solutions if gamma is equal to 0, then this is not true. Solutions are not C2, not even C11. But if you didn't like the result analytically that I showed you, let me show that this is in fact an interesting, a very remarkable result. It's a joy. I can see the Laplacian, the Schauder estimates is a perturbation theory. So everything goes into the Poisson equation. So if you understand that, you probably can show the more general result that I showed before. But so one way to understand the Schauder estimate is the following. I'm saying that the Laplacian of u is a Hilbert continuous function, and I'm telling you that u is C2 gamma. In other words, the Haitian of u is also Hilbert continuous. So in other words, what I'm saying is that if you add the diagonal of the Haitian, and this sum is a Hilbert continuous function, notice that here I'm not even asking for each one of them to be Hilbert continuous separately. There could have been some cancellation when I add them up, but if that happens, then Schauder estimates tell you that all the indices are C0 gamma. Okay, so even indices that doesn't appear on the equation automatically becomes C0 gamma. Okay? But as I said before, it's a perturbation theory. Okay? It goes from the Laplacian. It's the understanding of the Poisson equation, the Laplacian. But again, what is very remarkable from the PDE point of view is that with a very, very low information on the coefficients, you still have a very powerful compactness result. That's what I'm calling two theorems, one lesson. The first theorem was proven by D. George in 1956 and also approved by John Nash and Moser. So that more or less came from 56 to 61. They are independent works. And the second theorem is a result due to Krylov and Safanov, 79 and 80, which tells us that solutions to an elliptic PDE, regardless smoothness properties or continuity properties of the coefficients, have a universal modulus of continuity. Okay, so this is a very deep, very powerful concept. Okay, so this is particularly very important when you study homogenization problems. And in fact, this is so powerful that it's in fact, you should not see that as a linear result. This is more like a nonlinear theory. So let me say a few words about the nonlinear elliptic PDEs. So again, the nonlinear PDEs, it breaks into two main streams. The first one is in divergence form, where you have equations of this form, divergence of some vector field A applied at the gradient of u. So the prototype is what people call the P-Laplacian, okay? So the P-Laplacian, you notice that, it is elliptic, it has some ellipticity, but the ellipticity degenerates because when the gradient of u vanishes, you lose the information, you lose the diffusion. And also, there is the theory of the non-divergence form equation, which is the theory of fully nonlinear PDEs. Okay, and one example of an equation of that form is like these extreme Pucci operators, where you take a matrix, you divide the negative eigenvalues of the matrix, and then you add them up and multiply by some constant, and you take the positive eigenvalues, add them up, and multiply by a different constant. This is a completely fully nonlinear equation with many, many applications. And as I said before, that two theorems, one lesson is indeed a nonlinear device. And in fact, Ureltseva in 68 proved that p-harmonic functions are C1 alpha for some alpha. And Caffarelli in 89 proved that solutions to a general fully nonlinear equation is C1 alpha. Okay? So this is based on the George approach, and this is based on Krylov-Safanov-Harnack inequality. Okay, so equations without coefficients, even in a very general nonlinear setting, are C1 alpha. Okay, so now let me talk a little bit about free boundary problems. This is more or less the end of the first part of my talk, where I give an overview on elliptic PDEs. And now we still be into elliptic equations, but now things are going to get slightly more sophisticated, and I will explain why. So if you are talking about, in a broad talk, if you are going to talk about free boundary problems, the first one that you should talk about is the obstacle problem, because probably is the most well-known problem of free boundary type. So what is the free boundary? What is this obstacle problem? The problem is very simple to state, and there is many applications in finance, mathematics, and so on. But basically what you are trying to do is you have an elastic membrane, which is attached to some fixed boundary, and you would like to understand how this membrane adjusts itself when you push it against some obstacle, okay? So this is the idea that you should have in mind. You have an obstacle, and you have a membrane, and then you would like to see how that the displacement of the membrane, how it's going to adjust when it's against the obstacle. Okay, so the mathematical treatment of this problem is not hard to state, because this is a membrane problem. So the membrane is going to try to minimize the energy to have a stable position. So this function, the solution of that problem, is going to minimize the energy, as in the elasticity theory, but it's constrained to live above the obstacle. Okay? So that forces the problem to have a free boundary, and this is what I would like to explain. So this problem, from the mathematical point of view, is not very hard to be treated. Like the soft analysis involved is not that hard. It's fairly simple to show that this problem has a unique solution. I can always do upward perturbations because the obstacle is below. I can always perturb my membrane upward, which tells me that the membrane is going to be a superharmonic function. The Laplacian is going to be non-negative everywhere in the sense of measure. But as soon as the membrane separates from the obstacle, I will have some room. I have a decent distance from the membrane to the obstacle. I can do small perturbation downwards as well. So that tells us that the equation that is in the elasticity theory, like Laplacian of u equals to 0, is satisfied as soon as the membrane leaves the obstacle. Okay? So here you see that the equation is satisfied, but you don't know where. Because the equation, Laplacian of u equals to 0, it's satisfied on a set that depends on the solution itself. Okay? So this might sound naive at this stage, but it does include a lot of difficulties in this study. So the picture is more or less like this. Okay? You have, it's harmonic, and there is the contact set. So just a few properties. Just because it's in touch with an obstacle, the regularity issue that harmonic functions are C infinity drops to C11. This is the optimal regularity. Solutions to the obstacle problem cannot be better than C11, even if the obstacle is an analytic function. Okay? So this, you already see a major difference. And in fact, there is another issue that it's very delicate to be analyzed, is the regularity of the boundary of the contact set. So you want to understand what's the trace that the membrane leaves when it lifts up from the obstacle. And that was done by Luis Caffarelli in a very famous paper in 1977. And one way to understand the obstacle problem, you can call V the difference, like the difference from the membrane to the obstacle. And then you find out that this is the equation that this auxiliary function satisfies. Laplacian of v is some function of x, which is basically the negative Laplacian of the obstacle times the characteristic function where v is positive. So here you see that regardless the smoothness of f, the right-hand side is just going to be a bounded measure, okay? So you are in that borderline condition where you cannot apply Schauder theory, okay? So this is just a bounded function, okay? So indeed, to show C11, it requires some additional tools. Okay, let me mention another obstacle problem that I like a lot. There's a lot of interpretations of jet and cavity problems. I'm going to show you one that I particularly like. It's the following. This is a very physical problem that everybody can have intuition on. I give you a heated body, D, and then one seeks for an insulation of this body, okay, with some prescribed volume, probably, so that the heat flux is constant along this boundary. So here you see that it's a genuine free boundary problem. The problem here is precisely the insulation. That's your unknown, okay? So the picture I would like you to have in mind is this. You have your domain D, and here's the temperature. So here's where the temperature is positive. Here I'm insulating, so I'm saying that U is 0 outside. And the heat flux is the normal derivative of the temperature. I would like to say that this is identically 1, okay? So if you look at the temperature, so suppose that you know how to solve this problem, the temperature U is going to be harmonic in the set of positivity. It's clearly harmonic outside because it's identically 0. And in the sense of measure, I can say that the normal derivative of U along this free boundary is the Laplacian, okay? This is divergence theorem. So in the sense of measure, the Laplacian of U is going to be 0 everywhere, but along the free boundary, which it charges 1, okay? So if you force a little bit, you can say that this problem is related to this very singular equation where the Laplacian of U is the Dirac mass applied at U. Okay? It might not make much sense, but this is more or less what you are trying to do from the physical point of view. Okay? And in fact, this problem can be treated variationally, and this is how the problem goes. You want to try to understand this problem, even though this doesn't make much sense. The antiderivative of the Dirac mass is the Heaviside function. So it shows you that if you study this discontinuous functional, you have the hope that minimizers of this problem would be related to that equation. Even though this equation doesn't make mathematical sense, you would expect that. And in fact, that's what Luis Caffarelli and Alt did in the beginning of the 80s. They studied this functional, which it cannot be treated from the classical calculus of variation theory, but they were able to show existence of a minimizer. This minimizer, in fact, is harmonic in the set of positivity, and it's Lipschitz continuous, and this is the optimal regularity expected. And also the free boundary, that blue boundary that I drew before, is in fact a smooth surface up to a negligible set. And along this smooth part, it does solve U nu equals to 1 in the classical sense. Okay? So the free boundary problems that I showed so far, they have one feature. They are just one phase. So solutions, the obstacle problem is above the obstacle, and this problem, per the physical interpretation, the temperature is a non-negative quantity. But you can also think about problems that change phases. Okay, this is more related to Luis Caffarelli's plenary talk on Tuesday. So the picture one should have in mind is this. You have a region, this is your domain, and then you are trying to find a function U which will have a positive part, a negative part, and you are prescribing some PDEs which are involved. It's based on the model that you are studying in each phase of the free boundary, but you are also prescribing a flux balance along the interface, okay? So that's the general problem that you have. And this problem it's considerably more difficult than the one-phase problem. And this was, the first result in this direction was done by Alt, Caffarelli, and Friedman when they introduced this monotonicity formula. And this was in '84, where the governing operator is the Laplacian. Okay, a few years later, Luis also developed a very general existence and regularity theory for this type of free boundary problems, and they can afford elliptic equations in divergence form with Hilbert coefficients. Okay, several years passed until Caffarelli, Jørgensen, and Koenig were able to develop a it's almost monotonicity formula to be able to treat equations of this form, Laplacian of U plus some bounded source. It's impressive, it's remarkable and then you see how delicate these problems are. From passing from this point to that point, it's a huge, huge difference. Okay, you may think that you are just adding some small perturbation, it's a bounded function, but in fact it's a much, much harder problem. And in fact, you can also afford like Hilbert coefficient equations with bounded sources, and this is we did a few years later. Now, I would like to show an even more realistic problem. This is an ongoing project with a PhD student in Fortaleza. So now the picture is like, I took these eyes from the internet. So now the picture is the following. You have a cube of ice, which is probably made out of water, and then you're going to put inside some fluid or some juice or some scotch, depending on what you like to drink. And what's going to happen is that the properties of the ice are different from the properties of this different fluid, okay? So in fact, you should have different operators in each phase, okay? So you have an operator that accounts the properties of the water. This is probably going to be the Laplacian, but you have another operator, A plus, that governs the temperature when the temperature is positive, okay? And as you can imagine, if you add just a bounded function, the problem became much harder. This is the case again. It's another jump of difficulty. And of course, you have a prescribed flux balance again, which in this case must be the A plus normal derivative of U minus the A minus normal derivative of U should be constant. Okay, that comes from the model. So this is ongoing results with a PhD student in Fortaleza. We were able to show existence of a minimum. This problem can be treated variationally. So you set up a variational, like a energy functional, and then you try to show existence of a minimizer and try to prove some regularity issues from that minimizer. Existence of a minimum is not an easy task because this functional turns out to not to be convex, okay? But we were able to show existence of a minimum, and we can show that like a universal compactness property, solutions are like in parallel to the George regularity theory. We're able to show that minimizers of that functional are C0 beta or some beta. But we are very far from the Lipschitz estimate that all the other problems had. However, it does grow linearly away from the phases. And what we were able to show was what nowadays is called Kords-Nirenberg type of estimates, is that if you think a little bit, you have your ice melting inside a fluid. So after a while, this water is mixing up with your drink. So your drinking is getting more, the properties are getting closer and closer to the properties of the pure water. So it's reasonable to say that the norm, let's say the L2 norm of these two matrices are not going to deviate much. In this case, we can show an asymptotically optimal estimate, Solutions are asymptotically Lipschitz. It's not exactly Lipschitz, it's C0 alpha for every alpha less than 1. And it's still an open question, we have no idea how to show, is that if you assume that these matrices are Hilbert continuous subtly, is the minimum Lipschitz. Okay, so that we are very far from showing. Okay. But at this point, all the free boundary problems that I showed, the new and the old and the new, they were treated variationally. But there are many problems in real life that it comes with a non-variational structure. And the simplest example one can think of is that you have the Laplacian plus a drift term. So if you have a drift term, you cannot set up a functional so that the minimizers are solutions to that equation. And a genuine example is that if you would like to develop a fully nonlinear theory, okay? For instance, let me mention this problem. It's, for instance, that insulation problem. If instead of the Laplacian, the problem is governed by a fully nonlinear equation, the equation should be this. You have f of d squared of u, which is a very general fully nonlinear equation, equals delta naught out of u. Okay, if this didn't make sense for the Laplacian, where you have measured language, imagine here. Okay, this doesn't make any sense from the pointwise or any sort of meaning. But here are some heuristics, is that in the variational theory, we saw the Dirac mass as the derivative of the Heaviside. And then people developed the theory based on this perspective. But there is another way of looking at the delta Dirac mass. You can also, this is probably the most colloquial way of looking at the Dirac mass, is that Dirac mass is the limit of a sequence of functions that are concentrating the mass at one point. Okay, so this is the general picture that keeps the measure, like the L1 norm equals to 1. So in fact, if you would like to address a non-variational cavitation problem, what you should do is to study a singular perturb equation. Like now, for each epsilon fixed, I can make very good sense of this equation. This has meaning. I can try to solve. I can try to show that solutions are continuous or Hilbert continuous or C1 and so forth. But what I would like to understand as a cavitation problem is the limit as epsilon goes to 0, which accounts into proving a uniform in epsilon estimates. Okay, you'd like to prove geometric and analytic properties that are uniform in epsilon. Okay, and in fact, you can treat that in a more general setting. You can actually study a continuous family of free boundary problems that goes from the cavitation problem to the obstacle problem. And this was some projects that took maybe 5 or 6 years to be implemented, and we did with 2 students in Fortaleza. Is that we can study equations of this form. When gamma is equal to 0, you have the cavitation problem. When gamma is equal to 1, you have like a version of the fully nonlinear obstacle problem. And for each gamma in between, this is a model for gas in catalysis. It's called quenching type problems. I don't want to enter much of that. But the picture is this. Now, your free boundary problem has been turned into an equation, like you have a fully nonlinear equation or your favorite equation, equals to a negative exponent of u. Okay? So when u vanishes, the equation itself forces the Haitian to blow up. Okay? So what these problems understanding precisely the geometry of these free boundary. It's how to understand precisely how u hits the floor. Okay, so this is and then study the smoothness properties of this setting. Okay, but I don't want to enter much on that. So now I start my third part of my talk, it's at this stage, what I have shown to you is like how free boundary problems can be related to singular PDEs. So you have a free boundary problem that comes from a physical model, and then you end up studying some singular equations. And from this point on, I would like to reverse the perspective. Now I'm going to take classical equations from the PDE theory, and I would like to interpret them as a free boundary problem. Of course, when I do that, I'm extrapolating a little bit the physical meaning of free boundary, and try to basically import some free boundary tools, some free boundary technologies to study these equations. Okay, so there are several examples that fits into this philosophy. One of them is called MEMS type problems. It's equations that appears in that form. You have the Laplacian of u times a function f of u and f at 0 is 0. So again, when u vanishes, u loses the diffusion properties of the operator, and you'd like to understand how these things match. Okay, there is a very large literature on these kind of equations. And here, I would like to understand this is a free boundary problem, where the free boundary is precisely the points where u vanishes. Even very classical equations of the P-Laplacian type, I can see that as a free boundary if I want, because again, this equation, it's elliptic outside the singular sets of H. So when the gradient of H vanishes, I lose ellipticity, I lose the diffusion properties of the operator. So I would like to see that as a free boundary, where the free boundary is the singular point of the solution itself. So there are other examples, but even this one, like Poisson type equations, L of u equals g of x. I can try to understand that as a free boundary, again, extrapolating the meaning of the physical meaning of free boundary, and the free boundary here is going to be the points where the forcing term behaves like absolute value of x to a negative power, because understanding this beta here tells me precisely what is the borderline integrability condition for g. Okay? So let me show you one example where what you can do with this perspective is that you can develop like a Poisson type result in a very general setting for equations with borderline integrability conditions. So saying that f belongs to some space LQ is basically saying that f may blow up, but it blows up proportional to the absolute value of x to a negative power n over q. So this is the kind of results one can show, is that if q is less than the dimension of the problem, then solutions are Hilbert continuous. And this is the optimal estimate one can show. It's like C02 minus n over q, and this is optimal. Okay? When you increase q, f is getting better and better, so you should expect that the smoothness of u improves. And in fact, this is true. And if you would like to understand some continuity process on these sharp estimates. So when q goes to n, here you see that you get 2 minus 1, C01, which should be Lipschitz. Okay, so one would wonder whether solutions to an elliptic equation with ln sources should be Lipschitz. And this is not true, but it's almost true. And this is optimal again. Solutions are Lipschitz up to a logarithmic defect. Okay? And if you go up, solutions become C1, and this is the optimal estimate. And in fact, this result, this is encoded in Luis Caffarelli's 1989 paper. One can see that there. And again, in the dual version of this result, when q goes to infinity, so solutions are going to be bounded, you would see C11, but again, it's not true, and this is the optimal estimate one can show. Okay, so it's basically C11 up to a logarithmic defect. Okay, so of course in this talk I don't want to say much about the proofs of this result, but I think that it's a very reasonable wonder. It's how these kind of results are proven, right? So maybe in 1 or 2 minutes I just would like to give you the flavor of the geometric ideas behind of these proofs. And this is the setup. Okay, you have an equation that you want to understand the regularity issues of U, and after some like maybe some transformation, you can think that you normalize U is bounded by 1, and the norm, I don't even say which norm is here, but the norm of F in the space that you are studying is very small. Okay, so suppose that you can get into this condition. Okay, so saying that U is less than 1, the only information that is encoded here is that U is randomically distributed in this box. Okay, but it solves a PDE with the right-hand side that is close to 0. So one should expect that this is not harmonic, but it's close to a harmonic. So in fact, that's the first step. You show that there exists a harmonic function, H1, that and some radius r. So this, you discretize the problem. Some r, this is r is fixed, is a universal number, so that you will have to follow this harmonic function up to an error of order 1 plus alpha inside this ball of radius r. So what we have done at this point is that, remember that U would be randomically distributed in this box, but when you have this information, you have cleaned up this. There is no need to look for U in these regions, okay? So you will have to follow this path, so you forget about that. But this is a PDE, so I can always normalize this thing. So if I had my iPad here, I would just squeeze this to the unit ball, and then I would try to repeat the argument again. If you do that, you will probably end up with another harmonic function. It's not necessarily the initial one, but this one in the ball of radius r square, you will have to follow it up to an error of order big O of r square 1 plus alpha. And then you keep repeating these arguments, so you discretize and you keep repeating this argument. And of course, there is a technical issue, which is the convergence analysis of the linear part of those harmonic functions. Okay, that's slightly more delicate, but I don't want to bother you with that. And then if you repeat that infinitely many times, and you try to draw the graph of a function that is supposed to follow these linear parts of harmonic functions, whenever you enter into the next ball, dyadic ball, you'll see that this is C1 alpha. So solutions must be C1 alpha, and this limiting function is going to be the tangent plane at this point. So this is how these things go. Okay, let me show you another set of results that one can show is the theory of degenerate elliptic PDE. So think about the Laplacian that I showed you before in a non-homogeneous media. So you have some equation, you have some matrix Aij that take into account the inhomogeneity of the media. And this problem it's much harder than the linear setting. It's not basically because it's nonlinear. It's actually because there is a villain, which is, as I said many times, is the free boundary. It's the set where the diffusion properties of the operator collapses. Okay, so this problem, that's why this problem is much harder than the linear setting. And so there are few decades of studying this problem, and they always try to see what happens with the set where the gradient vanishes. And people always say bad things about the villain. This is our job. But I'm gonna do a bonus for the villain. So this is a result that we were able to show, is that if you have a weak solution to that equation with elliptic coefficients and just a little bit more than continuity, which is necessary, then at a critical point, so the point where the diffusion collapses, in fact, U is smoother than in other points, up to C11. So this is the solution is as smooth as solutions to the constant coefficient equation. Okay, so this is rather surprising, and I like this result, but I like even more when you revisit the Schauder theory, the first slide that I started my talk with. Okay, so here I put again the result in the non-variational setting is that, again, let me recall the Schauder theory says that if you have an equation with C0 beta coefficients, then solutions are C2 beta. This is a perfect result. Okay, it seems that there's no way to improve it. But if you try to import these free boundary ideas to study this problem, of course, there is no clear free boundary. The first problem, it would be more or less reasonable to expect that the critical points should behave like this abstract free boundary. But here, there is nothing. I mean, there is no degeneracy of the ellipticity, nothing. However, there is a slight room for improvement of the Schauder theory, and this is, it's not clear, but you can understand the free boundary as the point where the Hessian degenerate. So here's a theorem that one can show, is that if you have an equation of this sort with elliptic coefficients and slightly more than continuity, then at the point where the Hessian vanishes, the Hessian is asymptotically Lipschitz. So it goes from just being continuous to being almost Lipschitz. So this is it's a big step from the classical theory. So if you think just to give a perspective on like a graphical perspective, the Hessian in all the points should behave like this. It's a very like Hilder continuous or Dini continuous function, but if the Hessian vanishes, then it's a much smoother graph. Okay, so let me briefly mention that you can also have equations that it's in non-divergence form and also degenerates the ellipticity. This is the theory of non-variational degenerate elliptic equations. And ellipticity degenerates as a power of the gradient, as in the Laplacian case. And here it's clear that you should interpret the critical set as the free boundary. So there is a recent history of this problem that started in 2004 with some existence and some other properties of this equation. Things start getting more interesting in 2010 when Gonzalo Davila, Patricio Felmer, Alex Quas, and Imbert proved ABP estimates, Harnack inequalities, and some Hilder continuity of solutions of this problem. And very recently, Imbert and Luis Silvestre were able to prove that solutions are C1. So, in fact, solutions to this problem enter into this C1 regime. And what we were able to show with, again, two students in Fortaleza was that, in fact, you can write up the optimal estimate. Okay? So, in fact, solutions are C1, but they are C1 1 over 1 plus delta. And here you see the precise effect of the degeneracy of the ellipticity here appearing on the regularity theory of this solution. Okay, so this is interesting, and there are a lot of applications. I want to go very fast with that. Recall that p-harmonic functions are C1 alpha. 20 years later, people were able to prove that if the p-Laplacian of a function is bounded, then solutions are C1 beta. It's C1 alpha for some other alpha. And we were able to show that this in most of the cases is technical. It's like it holds in some particular cases. This is the optimal estimate. So solutions should be C1 1 over p minus 1. Okay, so it's a quantitative estimate on how smooth solutions whose p-Laplacian is bounded can be. Okay, and there is this other result. P-harmonic functions should most of the cases be C1 1/3. And this is not optimal if you fix P, but it should be optimal uniform in P. So if you have a model, you don't know which P you should take, go with C1 1/3, you should be in the safe side. This is basically the philosophical idea behind this theorem. So these results are proven when you basically pass the derivatives through in the definition of the P Laplacian. The P Laplacian, if you compute the derivatives, this is going to be like the gradient of u to the p minus 1 times the Laplacian of u plus this ugly term. And this ugly term in PDE theory has a name. We call it infinite Laplacian. So here's a concrete result with no technical issues hidden. So if you have an equation, so if you have a harmonic function whose infinite Laplacian is bounded, then the solution is C1 1/3. And this is optimal. So since I mentioned the infinite Laplacian, let me say that this operator is related to a very old problem of finding the best Lipschitz extension of a given boundary datum. So you have a function f defined on some domain, on the boundary of some domain. You'd like to find what's the best way of extending it in a Lipschitz fashion. So this can be treated in a PDE. There is a PDE approach for this problem, and this is precisely the equation involved. So the best Lipschitz extension solves this highly degenerate nonlinear PDE, which is called the infinite Laplacian. Okay, so this is a famous open problem in PDE theory, is whether infinite harmonic functions are C1. They are always Lipschitz because they are a Lipschitz extension. They are Lipschitz. But by getting the best Lipschitz extension, do I improve the regularity of it? So this is a very famous open problem. And here are some well-known results. This was proven in 2005 by Ovidio Savin in dimension 2. So in dimension 2, solutions are C1. Solutions are Lipschitz, so they are almost everywhere differentiable. But Evans and Smart were able to show that they are in fact everywhere differentiable. Okay? But we have known since the 60s that this function, x to the 4/3 minus y to the 4/3, is infinite harmonic. Okay? So this is the graph of this function. And ta-da, this function is C1 1/3. Okay? So this is the regularity. So why C1 1/3? In fact, there is no result at this stage that indicates that this should be like borderline regularity condition for solutions to these kind of problems. But I'm going to give you two concrete examples, and then I finish my talk. The first concrete example is the following. So suppose that you have a function, a best Lipschitz extension, let's call it h. So this is going to be infinite harmonic. And then I can approximate these functions by h sub p just by solving the P Laplacian equation inside your domain with the boundary data equals to h. So this h sub p will converge to h, and by stability, the infinite Laplacian of this approximation will have to converge to 0 because the limiting function is infinite harmonic. But with this soft analysis, you don't have a precise understanding of how fast this quantity goes to 0. But what I'm about to tell you is that if you give me a little bit more of information, I can tell you the regularity of your initial function. And this is the theorem, is that if the infinite Laplacian of these approximating functions is big O of 1/p, so it goes to 0, at least as fast as 1/p, then in fact your original function is C1 1/3. Okay? And just another, let's say, indication that maybe C1 1/3 is in fact an optimal result, let me mention the infinite obstacle problem. So what is the infinite obstacle problem? You have an obstacle, as in the classic obstacle problem that I mentioned before, and you would like to find a function that lives above the obstacle. It's always above the obstacle. It's infinite superharmonic everywhere, and solves the PDE whenever your function separates from the obstacle. So this is the infinite obstacle problem. Okay, so it's a non-variational setup for the obstacle problem that I mentioned earlier. So this is the picture. So the governing operator now is going to be the infinite Laplacian. And here's the theorem that we were able to show with Giulio Rossi and José Miguel Urbano from Coimbra. is that the solution to the infinite obstacle problem is precisely C1 1/3 along the free boundary, in the sense that it leaves, it separates from the obstacle precise as a graph of a C1 1/3 function. So in the sense that you can, at each point of the free boundary, you can put like a barrier of order distance to the free boundary to the 4/3 above and below. And I think this is a good place for me to stop. Thank you so much.
Are there any questions, comments?
Is anybody looking into the associated time-dependent problem, the parabolic problem?
No. I haven't. Well, we do have one preliminary result with José Miguel Urbano on sharp estimates for p-parabolic equations, but it's basically all open for the evolutionary problems. It's very interesting to look at. Thank you, Elena.
More questions? Then let's thanks again.
Thank you.